Dear learners, welcome to NIOS Studio. Today, I, Piyush Bansal, am going to take your lesson on differential equations. Differential equations occur naturally in many phenomena in real life applications, such as in the area of mathematics, physics, biology, and other sciences. So, it came into existence with the invention of calculus, so which was early in 1665. This is derived from the relationships involving the rate of change, such as those found in calculus in mathematics, physics, and other sciences. It can be formed by looking at the relationship between the function and its derivatives. So, firstly, this was invented by an English physicist, Isaac Newton, in 1971, who solved these three types of differential equations using infinite series. Here, this function y represents a function of variable x. So, y will be called a dependent variable and x is an independent variable. F here is a given function of x. In the second equation, f is a given function of x and y, and dy by dx is the derivative notation again of y with respect to x. And in the third equation, the dependent variable y is a function of two variables x1 and x2. And later on in 1696, this was independently invented by a German mathematician, Leibniz, who solved this differential equation dy by dx plus pxy equal qxy to the power n. Here p and q are given functions of x and n can be any real number. Such differential equation we call it as Bernoulli differential equations. Now, looking at the derivative thing, just for a recap. So, dy by dx is nothing but the rate of change of a dependent variable y with respect to the independent variable x. So, such derivatives equations which involve derivative are frequently used in describing the changing universe. So, whenever we talk about rate of change, then comes the derivative notation. Now, this is the formal definition of differential equation. So, any equation which contains independent variable, dependent variables, and the derivatives of dependent variables with respect to independent variables will be called a differential equation. Now, in our course, we will going to study about ordinary differential equation. So, ordinary differential equation basically is an equation which contains only one independent variable, only one dependent variable, and the derivatives of dependent variable with respect to independent variable. So, for some examples, so if we consider the first example, dy by dx equal 4x minus 2y plus xy. This contains the independent variable over here, which is x. Then it contains a dependent variable y with respect to x, and derivative is there dy by dx. In the second equation, we can see dx by dt plus dy by dt equal x plus y minus t. So, here x and y are two dependent variables, t is the independent variable. So, by the definition, if you look carefully of ordinary differential equation, it should contain only one dependent variable and one independent variable. So, looking at that definition, we can see that this option A is the ordinary differential equation, whereas option B is not an ordinary differential equation, because it has two dependent variables x and y of the variable t. Now, okay. Looking at the next thing, which is order of a differential equation. So, order is defined as the order of the highest order derivative of the dependent variable with respect to the independent variable involved in a differential equation. So, order we can see is always a positive integer. So, as an example, if we look at this first differential equation dy by dx minus cos x equals 0. So, it involves this dy by dx term, which is the first order derivative of y with respect to x. So, this will have order 1. As for second example, d2y over dx square whole square plus cos of dy by dx equals 0. So, if we look carefully, this is again a differential equation as it involves the derivatives and the function y and x, and here dy by dx is the first order derivative, d2y over dx square is the second order derivative. So, since the highest order derivative present here is d2y over dx square, which is of order 2, so this differential equation has order 2. Similarly, in the third case, the highest order derivative present here is of order 3, d3y over dx cube. So, this has order 3. And the next one again, so since it has the maximum highest order derivative, which is dy by dx, so this will have order 1. Now, next definition is the degree of a differential equation. So, if a given differential equation is a polynomial equation in derivatives, this is important here, in derivatives. So, it should be a polynomial equation in the derivative part, then the highest power of the highest order derivative involved will be called degree of that differential equation. So, again this is always a positive integer. Now, it is not always possible to have a differential equation involving derivatives to be a polynomial equation. So, it is not always possible to have a degree. So, order is always defined, but degree may not be defined. So, if a differential equation is not a polynomial equation, then the degree of that differential equation will not be defined. So, like in this first example, again dy by dx minus cos x equal to 0. So, this has the first order derivative, highest order derivative is dy by dx, and the power of dy by dx is 1. This is a polynomial equation in dy by dx derivative. So, this will have degree 1. In the next example, this one has dy by dx term coming as the angle of the cosine function. So, its degree will not be defined. So, this is not a polynomial equation in dy by dx. So, degree is not defined. In the third example, if we look carefully, this is d3y over dx cube minus dy by dx to the power 2 by 3 equal to 0. So, if we reduce it further, if we take dy by dx to the right side and take cubes on both sides, so it will reduce to this equation, which is d3y over dx cube whole cube equal dy over dx whole square. So, now this has become a polynomial equation. The highest order derivative in this equation is d3y over dx cube, which is of order 3, and its power, highest power of this is 3. So, this will have degree 3. In the next example, again when we have sin x plus cos dy by dx equal to y square, this again appears to be non-polynomial, since dy by dx is coming as the angle of cosine function. So, if you compare it with the second example, in second example we could not separate dy by dx, but in the fourth one we can reduce it further to dy by dx equal cos inverse y square minus sin x. So, this will become a order 1 and degree 1 differential equation, because this is now a polynomial equation in the derivatives. This thing you cannot do with the second one. You cannot separate out dy by dx and make it a polynomial equation. Okay. Moving on, the next is the concept of solution of a differential equation. So, there are multiple ways where we can find a solution of a differential equation. So, let us look at the formal definition first. What do we mean by solution? So, it is a relationship between the dependent and independent variables that satisfies the differential equation. So, such a relationship will be called the solution of that differential equation. Solution, just like consider the differential equation d2y over dx square plus y equal 0. This is again second order, because second order derivative is the highest order derivative present here, and this is again a polynomial equation in d2y over dx square, the derivatives. So, the degree of this differential equation again is 1. Now, if we can check that, we will see how we will get the solution later on, but we can check that this y equal a cos x plus b sin x will satisfy this differential equation. So, here a and b are arbitrary constants or unknowns. So, this will be called a solution of this given differential equation. Now, solutions can be of different types. The first type is general solution. So, general solution basically is a solution of a differential equation which contains as many arbitrary constants as the order of the differential equation. Just like here, if you look at the previous example itself, d2y over dx4 plus y equals 0, then here the order here is 2, order of this differential equation. So, its general solution will contain 2 arbitrary constants, just like the case over here a and b. A and b are 2 arbitrary constants. It can take any arbitrary values. So, this will be called a general solution of the given differential equation. Okay. So, next type is particular solution of a differential equation. So, in this case, it is again a type of solution of a differential equation which can be obtained by giving some particular values to the arbitrary constants in the general solution of the differential equation. So, just like again if we look at this example, so d2y over dx square plus y equals 0. So, earlier we were using y equal a cos x plus b sin x, a and b were arbitrary over there. So, in particular if we take a equal to 2 and b equal to minus 3 in the general solution, then this will be a particular solution of the given differential equation. So, basically a basic idea is that the particular solution is a solution free from arbitrary constants. So, there will not be any arbitrary constants involved in the solution. So, it is a solution without any arbitrary constants. As for another thing, when you take a as minus 1 and b as 0 in the general solution, then we get y equal to minus of sin x. So, this is again a particular solution of the given differential equation. So, we can note one thing from here, that this 2 cos x minus 3 sin x is a particular solution and minus sin x is also a particular solution. In particular, you can assign any arbitrary values to the constants a and b. So, which means we can have arbitrarily many uncountably many particular solutions. So, basically particular solution of a differential equation is not unique. So, this can be noted. Now, formulation of a differential equation. So, formulation like some curve is given to you, some function is given to you. Now, what you want to do is you want to find the differential equation which has that solution curve. So, here we as per your syllabus will look for the 3 types. Type 1 will be when particular solution is given to us. Type 2 will be when general solution with one arbitrary constant is given, and type 3 is when general solution with 2 arbitrary constants are given. So, we will see quickly one by one. We will start with the type 1 when particular solution is given. So, basically some solution without any arbitrary constants will be given to you. You will be supposed to find out the equation involved, the differential equation involved. Okay. So, let us look at that first case. So, what we do in general in such cases is, in such problems the given solution does not contain any arbitrary constant, and solution can be found out by differentiating the given solution to get the required differential equation. So, as for example, we can see that the function y equal root of 1 plus x square is a solution of dy by dx equal xy over 1 plus x square. So, basic idea over here is just to differentiate the given function y equal root of 1 plus x square and to get this differential equation. So, here is a quick solution to this problem. So, we have the given function y equal root of 1 plus x square. We simply differentiate both sides with respect to x to obtain dy by dx equal x over root of 1 plus x square. Then we since we have to obtain differential equation of that form, so we just multiply numerator and denominator both with root of 1 plus x square, and then we replace the value of root of 1 plus x square with y to obtain the final solution, the final differential equation over here. So, we can see that this solution satisfies the differential equation dy by dx equal xy over 1 plus x square. As for next example, this y equal e to the power minus 3x is a function which will satisfy this second order differential equation. So, this is a quick solution again. Given function is y equal e to the power minus of 3x. So, we differentiate it once, we get dy by dx equal minus 3 of e to the power minus 3x. Okay. So, since in the question they are asking you to prove that this particular solution is a solution of the second order differential equation, that is why we are doing it 2 times the differentiation. Otherwise, if they ask you the differential equation involved for this function, it could be a first order, second order, third order, and so on. Okay. So, since they are asking you to prove it for the second order, we differentiate it again with respect to x in order to obtain the final differential equation. So, steps are over here. Now, the second type is when one arbitrary constant is given to you. So, you have a general solution which contains one arbitrary constant, and you are supposed to find out the differential equation involved here. So, these are the steps involved here. So, what we can do is if the arbitrary constant of the general solution can be separated, then just separate it out and take the differentiation on both sides, so that the derivative of that arbitrary constant will make it 0. So, the resulting differential equation will be free of any arbitrary constants. So, basic idea is to remove the arbitrary constants in order to obtain the differential equations. So, okay, if it is not possible to separate out arbitrary constant, then what we can do is just differentiate it both sides and evaluate the value of that arbitrary constant, and whatever value you obtain, you just substitute that value in the given solution, and that will make the equation to be constant free. So, that would be a resulting first order differential equation, and since this contains only one arbitrary constant, so the resulting equation will be of first order. Now, these are some of the spatial curves of type 2, like first one, equation of family of straight lines passing through the origin. So, this will be y equal to ax. Second family is the family of concentric circles which are centered at origin and having different radii. So, center is fixed here, radii can vary, fixed at origin, so, and radii is varying. So, this will be of the form x square plus y square equal to a square. Again, only one arbitrary constant here, which is a. Now, equation of family of circle which touch x axis at origin. So, such equations are nothing but equation of family of circles passing through the origin and having center on the y axis. So such equations will take the form x square plus y minus a whole square equal to a square. So we can see that again only one arbitrary constant is involved, which is a. In this third case, we won't be able to separate out this constant a. In first two cases, a can be separated, but not in the third one. Fourth curve is equation of family of circles again in the first quadrant, which is touching both coordinate axes. So x minus a whole square plus y minus a whole square equal to a square. This will be the form. So again only one arbitrary constant a is involved. And another family is the family of parabolas having vertex at origin and axis along the positive direction of y axis. So such family will be of the form x square equal for a y. So again a is the arbitrary constant here. So our aim here is to remove this arbitrary constant from whatever solution or whatever family of curves are given to you in order to obtain the differential equation of the first order. So like here, this is the family of concentric circles having center at origin and radius arbitrary a. So this is the way we can find it out. Since a is already separated, a square, so we just differentiate both sides in order to obtain 2x plus 2y dy by dx equal to 0, and this will give us the resulting first order differential equation for the given family of concentric circles. Similarly, when we have this equation y square equal x minus a whole cube, then again a can be separated out. So we can have we can take 1 by 3 on power on both sides, which gives us y to the power 2 by 3 equal x minus a. Now a is separated, so we can differentiate directly in order to obtain the resulting differential equation of first order in this case. Now this is another family y equal a sin x. So again a can be separated by y over sin x equal to a, and then we can take differentiation, or we can do it this way also. Rather than separating just like the second case, it said just take the differentiation, find the value of a and put it in the given equation. So this is what we are doing over here. So y equal to a sin x, we differentiated directly on both sides. So we get dy by dx equal a cos x. Now a value is from 1 is y over sin x, so just replace that value and we get the equation without any arbitrary constant. So this is the resulting differential equation of the first order for the given family of curves. Now differential equation of the family of lines passing through origin, we saw that this will have the equation of the form y equal to ax with a as the arbitrary constant. So just take the differentiation again on both sides, we get dy by dx equal to a and replace the value of a again from equation 1 to obtain the resulting first order differential equation for the given family of lines passing through origin. Now moving on to type 3, when two arbitrary constants are given. Now since we have two arbitrary constants, so when we remove these two arbitrary constants, the resulting differential equation will be of second order, of order 2. So when the general solution with two arbitrary constants is given, the corresponding differential equation is of order 2, and for the given solution we differentiate it twice and remove both the arbitrary constants to obtain the resulting second order differential equation satisfying the given solution. So these are some spatial curves again. Equation of family of straight lines in general is given as y equal ax plus b. A is the slope, b is the y intercept. So this is slope intercept form of the equation of family of lines. Then family of circles having fixed radius r and arbitrary center a comma b. So this is the resulting curve x minus a whole square plus y minus b whole square equal r square. Now, equation of family of parabolas having their axis of symmetry coincident with x axis will be given by y square equal to 4a x minus b. So, again it has two arbitrary constants a and b involved. Next is the family of ellipses having center at origin and axis coincident with the coordinate axis. So, this will be again of the form x square over a square plus y square by b square equal to 1. A and b are arbitrary constants here. Similarly, family of hyperbolas having foci on x axis and center of origin center at the origin, this will be given by x square by a square minus y square over b square equal to 1. So, two arbitrary constants again involved. So, let us look at it quickly, how to find the differential equations involved for such curves when we have two arbitrary constant involved. So, like first example is find the differential equation of all non-vertical lines in a plane. So, being non-vertical, it will have some slope a and y intercept will be b in this case. So, this will be of the form again y equal a x plus b. Now, it contains two arbitrary constant a and b. So, we have to differentiate it twice and remove both the arbitrary constant to get the resulting equation. Now, since b is separated, we can differentiate. The process here is to separate one variable at a time and then take differentiation on both sides. So, that one of the variable is gone when you differentiate it. So, when we differentiate it once, so b is removed, we get dy by dx equal to a. Now, a is separated already. So, we differentiate it again on both sides to get d2y over dx square equal to 0. So, this is the resulting second order differential equation for the given family of all non-vertical lines in a plane. As for second example, it is asking to form the differential equation representing the family of parabolas having their axis of symmetry coincident with the x axis. We just saw that such equations, such family will satisfy the curves y square equal 4a x minus b, where a and b are arbitrary constants. So, again we just separate out one of the variables. So, just multiply this 4a inside. So, 4ab will separate out b constant. Now, we differentiate it on both sides in order to obtain 2y dy by dx equal to 4a, which in turns gives y dy by dx equal to 2a. So, again now a is separated. So, we directly take in differentiation on both sides. So, we obtain the resulting differential equation of the second order. Now, for the next example, they say write a differential equation for y equal to a cos alpha x plus b sin alpha x, where a and b are arbitrary constants. So, in this case again we start with the family of curves. So, either you can separate out one of the variable by dividing first by cos alpha x or sin alpha x, or we know that this has two variables a and b. So, we differentiate it twice directly because cos second derivative is again cos, sin second derivative is again sin. So, we can directly differentiate it two times in order to obtain the resulting differential equation of the second order. Okay. So, let us take a small break. We will meet in some time. Thank you.
जीवन ये प्रकाशित करने राहों को आलोकित करने,
जीवन ये प्रकाशित करने राहों को आलोकित करने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने।
अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने।
जीवन ये प्रकाशित करने राहों को आलोकित करने।
धन साधन समय की सीमा से विद्यालय जो मुक्त हो,
धन साधन समय की सीमा से विद्यालय जो मुक्त हो।
कभी पढ़े हम कहीं पढ़े, वे विषय की लोच से युक्त हो।
कभी पढ़े हम कहीं पढ़े, वे विषय की लोच से युक्त हो।
मित्रों हम उठे और जागे,
मंजिल आने की ध्वनि सुने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने।
जीवन ये प्रकाशित करने राहों को आलोकित करने।
राष्ट्रीय मुक्त विद्यालय का है द्वार खुला सबकी खातिर।
शिक्षा परीक्षा का अवसर एक बार ही क्यों मिलता फिर।
शिक्षा और परीक्षा का अवसर एक बार ही क्यों मिलता फिर। दुनिया में इसके केंद्र बात,
कोई मन चाहा केंद्र चुने। हम अपना दीपक स्वयं बने, हम अपना रास्ता स्वयं चुने। कोई मन चाहा केंद्र चुने।
Dear learners, welcome back to the session. So, we were discussing about, in the first session we discussed about finding the differential equation given the solution curve. So, solution curve was given to us initially, we were differentiating it to obtain the differential equation and we saw three types. Now, let us move on to the other way round. So, we will be given the differential equations and we will be asked to find out the solution curves. So, it could be a general solution to the differential equation or could be a particular solution giving some particular values to the arbitrary constants. So, let us see how we can obtain solutions of the differential equations. So, as per your syllabus, we have to discuss three things over here. So, first thing is the method of separation of variables, second would be the homogeneous differential equations, and third will be the case of linear differential equations. So, let us see one by one how we can find solutions for each case. So, now solution of equations of first order and first degree. A general solution, general differential equation of first order first degree will take the form as f of x y dy by dx equal to 0. It could be any function of the independent variable x, the dependent variable y, and the first order derivative of y with respect to x. So, these are the following three types that we are going to study. differential equations with separable variables, then homogeneous differential equations and linear differential equations. So, by differential equation with separable variables, we mean a differential equation where we can separate out the value the variables x and y. So, as we can see f x dx equal g y dy. So, left side of this equality contains only the variable x and right side of this equation contains only the variable y. This method is also known as method of separation of variables. So, this is how we solve such differential equations. So, first, given any differential equation, if it is a separable one, so just separate out variable x on one side and variable y on the other side. Now, since left side contain only the function of x, right side contains only the function of y. So, what we can do is we can simply integrate it on both sides with respect to the left side will be integrated with respect to variable x, right side will be integrated with respect to variable y. So, one thing we can observe from here, when you integrate the left side, we get a constant c, and when you integrate it with respect to y on the right side, again you get a constant of integration. So, we can club both the constants to get a solution of the form f x equal g y plus c. So, the constants appearing on both sides can be combined together to get only one arbitrary constant. And again, since this is of first order, because only dy by dx is involved, first order derivative. So, there will be only one arbitrary constant here in the general solution of such a differential equation. So, this is one such example. It says find the general solution of the differential equation dy over dx equal to 2x. So, as you can see here, we can simply separate out the values of the variables dy on the left side and dx on the right hand side to obtain dy equal to 2x over 2x times dx, and then we simply integrate. So, this is the solution over here, dy equal 2x dx, simply integrate on both sides and we obtain y equal x square plus c as the solution of this. Okay. Now, let us look at the geometrical meaning of such family of curves where we have y equal x square plus c. So, this c can be an arbitrary constant. So, one differential equation can have a family of curves as a solution. Okay. So, we can see that thing from here as we have the solution curve which is given by y equal to x square plus c. So, let us plot this solution curve. So, like if we take c equal to 0, we get y equal to x square as the function. So, the plot, this is a parabola passing through origin, upward parabola, it will have a curve given like this. When we take c equal to 1, the function becomes y equal x square plus 1. Its plot, this again is a parabola having vertex at the point 0 comma 1. So, you can see that this will be the curve. Then for c equal to 2, we will have this curve. When we take c equal to minus 1, now the vertex will shift to the negative direction. So, 0 minus 1 will be the vertex. Then with c equal to minus 2, this will going to be the curve. So, all these curves will satisfy the same differential equation, which is dy by dx equal to 2x. Okay. Why? Let us see that also. So, these are the 5 curves that we obtained just now. Just draw a vertical line through any point on the x axis. So, at that given point, the slope will always be dy by dx equal to 2x. So, we can see that from here, like for the first curve y equal to x square, at the point where it intersects the curve, this will be the slope, Similarly, for the next point, this is the slope, the next point, this is the slope, next point, and for the next curve again y equal x square minus 2, this will be the slope. So, in all such cases we can see that these slope lines, they are parallel, and slope, if you recall, is given by dy by dx, which is tan theta, and since the lines are parallel, so all the lines will make equal angles with the positive direction of x axis. So, the slope is same. So, for a given differential equation, we obtain the family of curves. So, we have arbitrarily many solution curves for the given equation. So, as for next example, we have to find a particular solution. Now, how to judge whether a differential equation will have a general solution or a particular solution? So, like if you see the previous case, so in this case the differential equation given was dy by dx equal to 2x. There was no additional condition given over here. So, which means we will not be able to remove this arbitrary constant because no initial value is provided. But in this problem, if you look carefully, the given problem is log dy by dx equal 3x plus 4y with the condition that y takes value 0 when x equal to 0. So, such problem, such initial value will help us remove that arbitrary constant and give a particular value to that in order to obtain a particular solution. So, for example, this is the solution over here. So, first we take this logarithm on the other side. So, this will become e to the power 3x plus 4y. Now, this is a separable one again. This is how we can separate variables x and y on both sides and simply integrate now in order to obtain this differential equation. Now, put the condition y equal to 0 when x equal to 0, and we can see that c will take the value minus 7 by 12. So, c is fixed now because of this condition, and when we replace this value of c again in equation 1, then we obtain the solution which is given by this. This solution you can see is free from any arbitrary constant c. So, this is a particular solution. So, we can obtain particular solution given a condition apart from the differential equation. Now, another form is reducible differential equation. So, these are differential equations having the form dy by dx equal the function of ax plus by plus c. So, we call them reducible because after substituting ax plus by equal to plus c as the another variable v again will be a dependent variable over x. So, basically we are removing this variable y, we are substituting in place of y. With this relation we get a differential equation, new differential equation in v, and that we can observe that will be a reducible, will reduce to variable separable form. So, this is one example of that type, dy by dx plus 1 equal e to the power x plus y. As you can see here, this x plus y is coming in the power of e, right. So, initially this is not a separable one, but what we can do is we can substitute here x plus y as v, and this will reduce this equation further to dv by dx equal e to the power v. Now, you can clearly observe that the variables v and x are separated. So, we can integrate now in order to obtain the final solution by replacing the value of v with x plus y. Similar is this problem. Here we have again 3x plus y plus 1 whole square. So, this 3x plus y plus 1 we will replace this with v in order to obtain the differential equation dv by dx minus 3 equal v square, and now it is again a variable separable equation. So, we separate out variable v and x on both sides, integrate them, and we will obtain the final solution curves. So, again there was no initial condition given with the problem. So, we will obtain the general solution with one arbitrary constant as the order of the differential equation. Now, second type is homogeneous equation. So, before going to the homogeneous differential equation, let us first look at what we mean by homogeneity in case of differential equations. So, homogeneous function basically is any function f which satisfies this relation that we replace this, just a second, sorry, break. Yeah. Okay. So, any differential equation which satisfies this relation f of lambda x lambda y equal lambda to the power n f of x comma y. So, here lambda is any non-zero constant and n is the degree, will be called the degree of that function. Okay. So, let us understand the definition with the help of some examples. So, if we consider the function f1 xy equal 5x square minus 6xy plus y square and f2 xy equal 6x plus 7y square, these are the two functions. Let us check which one is homogeneous and which one is not homogeneous. So, idea basically is simply to replace this x with lambda x, y with lambda y. So, in first case when we look at it, f1 lambda x lambda y will give me this 5 lambda x whole square minus 6 times lambda x lambda y plus lambda y whole square. From this entire equation we can find out, we can take this lambda whole square out and this will be resulting in lambda square times f1 of xy. So, we are having equation again of this form only, f lambda x lambda y equal lambda n f x y with n equal to 2 over here. So, f1 x y is a homogeneous function and its degree is n, which is 2 in this case. But for the second function f2, when we replace x with lambda x and y with lambda y, we are not able to obtain equation again in the form lambda to the power n f2 times x comma y. We will not be able to represent this function back again to this form for any number n, any natural number n, which means f2 is not a homogeneous function. Now, coming to the definition of homogeneous differential equation. So, any differential equation having the form dy by dx equal fxy over gxy or dx over dy equal to fxy over gxy, where fxy gxy both are homogeneous functions of order of same degree n. So, such differential equation will be called homogeneous of first order. So, if a differential equation is not homogeneous, we call it non-homogeneous differential equation. Now, this is the these are the steps involved to solve the homogeneous differential equations. First, express any differential equation homogeneous to the form dy by dx equal f of y by x by multiplying and dividing numerator and denominator both with x to the power n, where n is the degree of that function f and g being homogeneous functions. So, once the representation is there, you put y equal Vx and this will reduce this further to a separable differential equation, which was the first case, and we simply integrate it on both sides to get the solution, and finally, we replace v with y by x to obtain the final solution of the given differential equation. Okay. Same way, if your differential equation is of the form dx over dy equal fxy over gxy. So, earlier we put y equal to Vx, now equation is of the form dx over dy. So, we interchange the roles of x and y basically, and we put x equal Vy instead and proceed the steps as given above to obtain the solution of the given differential equation. So, as for example, we have the differential equation 3xy plus y square equal to 3xy plus y square dx plus x square plus xy dy equal to 0. So, in order to solve this differential equation again, we represent this equation in the form dy by dx or dx over dy. So, this is the first step that we do. Since if you look at it carefully, this is a homogeneous function again, both f and g. F function over here, this is of the form dy by dx equal to this. So, if you look at the numerator again is a homogeneous function of order 2, denominator again is a homogeneous function of order 2. So, this is a homogeneous differential equation. Now, being order 2, we divide this both numerator and denominator by x square in order to obtain this function on the right side, which is a function of y by x again. So, this is from step 1. Now, we put here y equal to Vx and we obtain the differential equation as a separable differential equation in the two variables v and x, which is given in the last step of this slide. So, being separable now, we will simply integrate it on both the sides in order to obtain this final solution as half log of v square plus 2v equal to minus 2 log mod x plus c, and finally replace v with y by x to obtain the final solution. This is again second example. Here we have x by y form. If you look at the power of e, this has x by y. So, instead of reducing it to the form dy by dx, we will reduce it to the form dx over dy. So, x will be treated as a dependent variable of the independent variable y in such a case. So, dx over dy equal to x by y minus half of e to the power x over y. So, again in this case we will simply replace, just a moment please. Okay. So, first we are checking that this is a homogeneous function. So, just go by the definition, f of lambda x lambda y equal to, we can see that this is turning out to be f of x comma y. So, here the power of lambda, because it has to be of the form lambda to the power n f x y. So, n here in this case is 0. So, this is a homogeneous function, and here again now we will replace x with v y and we simplify to obtain again a separable equation in v and y now, and we will integrate on both sides to obtain the solution. And since this initial condition was given, so we will obtain this curve. Now, final is this linear differential equation. So, linear differential equation in first order will be of these two forms, dy by dx plus py equal to q and dx over dy plus px equal to q, where in first case p and q are constants or functions of x only. In second case, p and q are functions of y or constants. So, these are the steps involved to solve it. So, in this case, first represent the differential equation in this form and find the integrating factor of the form e to the power minus integral p dx, and this is the general solution given by this relation in step 3. So, as an example, so take this function x dy by dx minus 2y, this is divide by x, we will get the linear form. Here p is minus 2 by x, q is 2x. So, we find the integrating factor, which turns out to be 1 over x square, and for the general solution like in the second case, here again x square is the integrating factor by going with the same steps, and this will be the general solution. So, just apply the formula, put the values, integrate, and you will get the general solution. So, the idea basically here is when we have differential equations, we can have two types of problems. One is when the solution curve is given and you are asked to find the resulting differential equation. So, in such cases, we will simply take derivatives on both sides with respect to x or with respect to y, depending over what kind of different solution curve is, and then remove the arbitrary constants involved and get the differential equation. Another way, the other way around, is the differential equation is given to us and we are supposed to find out the solution curves. So, depending over how many what type of differential equation it is, then we can apply that procedure and find out the solution curves involved, general solution or particular solution. So, I will stop here. I would like to thank you all for listening to me. Thank you.